We are.
Oh, great. All right, so hello and welcome to BELIV 2024. I was really hoping that I could say hi and welcome all of you in person in Tampa, but given the circumstances, I'm happy that we got to have a conference at all. So from the bat, off the bat, I would like to thank all of the conference organizers, tech people, and student volunteers, and whoever made this a possibility. Um, so BELIV is a workshop on like that has been going on for a while, and it focuses on discussing evaluations and beyond any types of methodology approaches that concerns visualization, from system design to research. It all fits here. It's the workshop happens every other year basically, and this is the 10th instance of the workshop, which means that it has been going on for 20 years. Yeah, it's quite crazy. So
Yay.
yay. Yeah, so if you have attended BELIV in the first or second time, and you're in the audience, please share your stories with us, and share any fun stories you have from BELIV in the past 10 years on Discord. So my name is Mahsan Noorani. I'm a research assistant professor at Northeastern University and Core Visualization Group. Along with my other seven other amazing people, we organized BELIV for you, Sandra Bay, Anastasia Bazarianos, Michael Correll, Kyle Howe, Jorgen Bernard, Dan Keefe, and May Elshehaly. I want to shout out to all of these amazing people because they have been working tirelessly for the past couple of months to make sure that this conference and this workshop gets here and in the best format possible. So shout out to all of you. So this year, BELIV had a theme of very timely theme of rethinking design, evaluation, and ethics in visualization in the era of generative AI. I think there are obviously a lot of classic papers from BELIV that you will see, but this topic itself has a lot of there are a lot of breadcrumbs from this topic around different papers and talks, the keynote and discussions that we will have later on. And aside from the fact that we are celebrating 20 years of BELIV, this year was amazing because we had a record 26 submissions. Woo! Each of the submissions that was reviewed by one OC member, and also two PC members or external reviewers. And finally, we ended up with having 17 finally accepted papers. These are great papers. I'm personally super excited for hearing about all of these brilliant people. So stay tuned throughout the day to listen to these talks. And special thank you to all the authors, whether or not their papers were accepted, who submitted to BELIV and made this workshop a possibility for us. And another thank you to all the other people from program committee members, external reviewers, and steering committee who just kind of provided their expertise, their support, their guidance and advice, and made sure that the conference, or let's say BELIV, I keep saying a conference because I feel like this year it's a mini conference on its own. But they made it a possibility. They volunteered their time or expertise, and we are so thankful for all of them. So thank you all. So going over the schedule, we kick off the workshop with the keynote, and then followed in this session by two papers, so kicking off the paper sessions as well. We will go for a 30-minute break. Coming back, we will have another paper session. But in this session, second session, basically we will have breakout rooms. So the breakout groups were basically originally designed for engaging the audience and making sure that everybody is on, from the audience to paper authors and all of the organizers are getting together and discussing timely topics that are emerging from the papers. unfortunately, because it's virtual, it will be virtual, but we're excited to make sure that we have that interactive engagement with all of you. So if you switch back to other workshops or other amazing events that are going on today, please make sure to be back around 11 a.m. Eastern time here. We will post a Zoom link in this page so that you can join and go to one of the breakout groups. And then we will go to lunch. Coming back in the afternoon schedule, we will have another paper session. It's a longer one to kick it off. After a break, we will have the final 4 papers. All of them are amazing, followed by another breakout group. These groups in the afternoon and in the morning, they are completely different topics. So make sure you come to both of them if you want to kind of connect with the audience and share insights and discuss these problems and challenges. All right, so without further ado, I would like to kick off BELIV this year. And it is with honor and pleasure that I introduce Dr. Simone Stumpf as our keynote speaker this year. Simone is a professor of responsible and interactive AI at University of Glasgow. But to be honest, quite frankly, she is a rock star in the field of human-centered AI and responsible AI. And her work has been extremely significantly for the past decade helping shape the explainable AI research through presenting and working on exploratory debugging approaches for interactive ML, and also providing design principles for enabling better human-computer interaction and investigating the effects of greater transparency. She also, aside from this track record of human-centered AI research, she also works on other topics that are including self-management systems for people living with long-term conditions, developing teachable object recognizers for people who are blind or have low vision, and also focused on investigating AI fairness. I think all of this research, what brings them together and what they have in common is that she thrives to empower all the users to use AI systems effectively. And today she's going to talk about how to empower stakeholders to assess AI systems. So without further ado, we're all excited for your talk. Simone, please take it away.
Great. Thank you very much. Let me just share my presentation. I hope you can all see that now. Let me just move various bits out of the way that might get in the way of this presentation. Right. Okay. So thanks for inviting me to give this keynote at the BELIV workshop at the Viz conference. We were just chatting earlier, and Viz is not my natural home in terms of conferences. It's the first time that I'm attending, so it's very exciting to talk to you. As already said, I'm Simone Stumpf. I'm a professor of responsible and interactive AI at the University of Glasgow. And I'm going to talk to you mainly about how to empower stakeholders to assess AI systems. So when I was invited, I was asked to think a little bit about the theme for BELIV. So I believe it's rethinking design, evaluation, and ethics in visualization in the era of generative AI. And when I was first thinking about that, I was going, oh, great, I just give them my usual spiel about explainable AI. So what I was going to do was talk about explainable AI, the vision that really was the basis for the DARPA call back in 2016. And of course, the today in this diagram was back in 2016, where The aim of the Explainable AI program was to develop this pipeline, or to turn the existing machine learning process or system into this explainable AI system, where you opened up the black box and had perhaps explainable models and explanation interface, so that the user could really understand the decision making or the behavior of the underlying AI program. And the whole point of this program was really to calibrate their trust. So the original call said something about appropriate trust, so that the user wouldn't over rely on the AI system, but also not under rely on it. So that's what we mean by calibrated or appropriate trust. Of course, there has been a lot of work to provide explanations, local and global ones. So local ones are that explain particular decision instances or predictions, quite often using Lime, for example. There's an example on the upper right about a visualization, really, about which features or pixels were particularly important in the decision making, that this was a wolf, right? I mean, you can clearly see it's not a wolf, it's a husky, but it's instructive to see, well, what does it actually rely on? And it's mainly sort of the surrounding snow rather than any of the features of the actual husky or wolf. Of course, you also have other visualizations, saliency maps, SHAP output, and some of these outputs, some of these visualizations are, as I said, local, or some of them are global explanations that try and prise open the model and give information about how the model works overall. Right. So, for example, you have this sort of SHAP output on here that says, well, these are the features, and the features have the following effect on the overall model. Okay. So I was also then going to tell you a little bit about my own work in explanatory debugging, particularly for interactive machine learning. And that is really where my work in explainable AI comes from. So what we were starting to do back in, it was actually before 2009, but that was when the sort of first comprehensive publication came out, and then it's sort of we built on that, and it resulted in the principles of explanatory debugging paper in IUI 2015 that then was cited within the DARPA XAI call. So what we wanted to do there was that we wanted to explain what the system was doing, which would hopefully lead to an improved mental model, increased satisfaction. But that was not all. What we wanted to do is give the user an opportunity to feedback or control the future behavior of the machine learning system. So so it was this sort of feedback loop where the system explained something, and then in a way the user explained something back. So and we also built visualizations. They were not very complicated visualizations because the target group for our explanations and systems were always people who didn't have a AI background, right? So they were people who might want to steer machine learning systems. So here's one that is actually coming from the IUI 2015 paper, and we called this system Elucidebug. And what you will notice is that it looks a little bit like an email client where you have a list of messages. We used 20 news groups, and it was 2 classes that we used, hockey and baseball. So you have a sort of original order, you have subject, you have a predicted topic, you have what we call a prediction confidence. So the probability that this predicted topic is correct. And then you have a sort of message pane where you can read what is in the highlighted message. So let me come back to these little arrows in a minute. We have other information. So sorry, in the message pane, they could obviously see what the message was. And then you notice there are some highlighted little bits here. And these highlighted little bits are keywords. So we trained a classifier, I think it was a multinomial naive Bayes. And from that, we generated explanations. So we had a sort of overall explanation here about why this hockey class was predicted, or the topic was predicted. And I just blown that out here, right? And one of it is about important words, i.e., you know, a sort of bag of words approach. And it says, well, this message has more important words about hockey than about baseball, right? And we color-coded them. And also, you will see that some of them are smaller. That indicates the relative weight. So the difference makes the computer think this message is 2.3 times more likely to be about hockey than baseball. And we also take the class distribution into account, right? And then we say, okay, this yields a 67% probability this message is about hockey, right? And again, just a little pie chart to represent the probability. Underneath is actually something far more interesting going on. So, and that will explain some of these highlighted words. So, we did some feature selection. We focused on the top 10 most important words. And what we display here is the importance of words. And if they are occurring in the message, they are highlighted, right? So here we have baseball, tiger, and hockey, right? And this is sort of blown up. So this, the bar chart is the relative weight or importance, as we called it, to that class. So in blue, we have hockey. And in green, we have baseball, and you can see that the word baseball is much more important for the baseball class than the hockey class. So, what does that have to do with interactive machine learning? So the user can build an understanding based on these explanations that we provided them, and hopefully they build what we call a sound mental model. So they understand how this algorithm, how the machine learning system works, and builds on that understanding. We allow them to feed back. So what they are able to do within this system is they can highlight words like this, and they can add them to these important words. So if you highlighted that and pressed a certain context menu, that new word would appear here. And then they are able to adjust the weights. So they can drag bars up and down to say this is the relative importance. And that would then retrain the machine learning model, and that is where these arrows come in. So that indicates that the confidence has either gone up or down since the last retraining. Okay, so all well and good. So I would have told you about that. I would have told you that, it's really a nice system and everybody should do explanations. I would have also gone on to talk really about problems with current explanations for generative or autonomous AI. So one of the problems is that explanations are currently often delivered as visualizations or in visual form, right? Everything I showed you just on the previous screen, if you were, for example, blind, you wouldn't be not able to use that. Or in certain situation where you don't have access to sort of a visual display, a good visual display. So we might have to switch to other forms of explanations. The explanations that I've shown you are meant to be pondered. You're sort of meant to engage with them. You're sort of reasoning with them. But how do we integrate that into real-time settings for human AI collaboration, right? So if you think, for example, that we integrate explanations into an autonomous driving vehicle, well, how would you need to change your explanations, especially your visual explanations, to make sense of what is happening? And then also, I would argue that currently we have a very narrow view of explanations. So I'm one of the people that really wants to broaden what we mean by explanations and what should be explained. And quite often what we actually want to have explained is why the model was developed in the first place, what decisions about the AI were made during its development, what training data was used to develop the model, how was the model evaluated, how good is it, and what biases or blind spots does it have. And all of these, or most of these, are not currently considered explanations as we know it. It's sometimes something that we really don't have a good handle on, and we can't sometimes generate it as part of the model development. We actually have to wait, or it's gone gone before the model was developed. So I would have delivered that, and I'm really bored of giving that talk. So I'm not going to do that, and instead I'm going to posit this. Current explainable AI approaches don't really consider enough why you explain, to who you explain, and how or what the effects of the explanations might be. So I thought I'll tell you about something else that's going beyond explainable AI, and really that has been the focus of my work for the last few years. And that is instead driving more around the assessment of AI. So I'm not too sure how many of you will be familiar with the EU AI Act that has just been ratified earlier this year. So it is legislation that will affect everybody that lives in the EU, but more importantly also any kind of software that or AI system that is sold into the EU. What that AI Act says is that all AI will need to be evaluated as to its risks. I added harm here because I think you can have low risk software that still has relatively high harm. So all AI systems will need to be evaluated, and if the risk is high enough, and the AI Act says something like AI systems that negatively affect safety or fundamental rights, then it might have to register with the EU and be assessed throughout its life cycle. And I underlined that here because when the AI Act was being put together and discussed, I was starting to wonder what that actually might mean, right? To be assessed throughout its life cycle, and how that might actually happen. So if you think, oh, I don't live in the EU, I'm not going to go and develop anything that is for the EU. Well, other regulatory frameworks are emerging. You had an executive order by the US president. You have regulatory bodies starting to think about assessing AI and actually evaluating it. So this is coming to a place near you. So what does it mean to assess, right? And currently we have the problem that assessments are typically done quite late in the development life cycle, right? You have if this is a sort of crude representation of an AI system development life cycle, you have typically evaluated around here, right? Just before you want to deploy it. Assessing it really rarely takes place here, right? There's also no systematic process to assess or audit. How do we assess? What do we assess? What standards do we apply? What tools do we use? So really nothing that can be or is developed to take place there. We have a lack of standards of what counts as good enough to pass an assessment on audit. And in a way, I think even if we had some standards, that might not necessarily answer all of our questions, because what counts as good enough might be different between different application contexts, right? So, for example, a clinical decision support systems, you might have to be make really, really highly accurate, whereas if you're thinking about something else, you might actually have a lower standard. It's further complicated that currently, when assessments are done, they are carried out by an AI expert, or in the case of a generative AI system, by red team. So where you basically put people in a room and tell them to bash away at a system to figure out the problems of it. And so stakeholders, especially those that are affected by the AI system, domain experts or end users or decision subjects, are really not usually involved in the assessment. So there's something really going wrong here in the assessment process. I want to take a few moments to talk about tools, especially visualizations that have been developed to actually help assess an AI system. So, for example, for AI experts, you have the What If tool or FairVis. And they have been around. Some people use them, but if you think about perhaps especially the FairVis UI, and to a certain extent the What If tool. The What If tool you really only can use if you know Python and you know how machine learning works. And then when you look at these visualizations for FairVis, you really have to figure out a little bit more about, well, you need to know a little bit more about the system than possibly the average person might know. So these allow you to assess fairness. There's another tool, FairSight, which is similar. It has sort of, you might have seen this and various bar charts, and I guess FairSight also uses some of these techniques to visualize what is going on in terms of fairness and distributions of groups and so on. You also have work that is trying to see how can you get domain experts or AI systems to evaluate fairness. And that is some of my own work. So here we actually developed a system that we then tried out with AI experts and domain experts to visualize what is going on in terms of fairness. So you have different visualizations, you have causal graphs, you have sort of distributions, you have simple bar charts that sort of visualize fairness metrics. And then people should be able to use that to make some kind of fairness assessment. This obviously has been also tried with stakeholders without a technical background, those people that are most likely not to be currently involved in assessing AI systems. So again, a sort of visualization is silver, and you will see that it also has this sort of causal graph explanation, and then again other visualizations about different fairness metrics on here. There's also a fairness elicitation interface that was presented in CHI back in 21. That again sort of visualizes some of the fairness metrics, or at least sort of helps people articulate what their fairness metrics are for a particular thing. In this case, it was child maltreatment cases, so social workers to articulate the fairness. And then again, I have worked on that a little bit. And so this is our system where we, in a way, applied our explanatory debugging approach to it. So we have various kinds of visualizations that allow people to find out what is happening within the system, and think a little bit more around biases. This doesn't necessarily spell out anything around fairness metrics. It's a very intuitive way of eliciting fairness judgment. But what we are able to do is take their judgments, their feedback back into the model and retrain it, and then hopefully make it fairer. So this is all good, but fairness is really only one aspect in responsible AI. We have a lot more, lot of other things that we would need to ascertain, and that is where I want to mention a project that has just been launched back on the 1st of May. It's going to run for just under 4 years. It's called Participatory Harm Auditing Workbenches and Methodologies, which I abbreviated to FOAM. And I apologize for that horrible acronym. So never let me near naming anything. But what is the point of this? What we want to achieve with that project is really that we want to empower some stakeholders without that technical AI background to assess or audit predictive and generative AI. And either they can do it by themselves sitting in front, or they can do it as a group. What we're going to do is we're going to do research around that, and we're going to use 4 use cases to do that. So health, media content, cultural heritage, and collaborative content generation. In all of these cases, so the health, it's a predictive system, for example, that predicts health risk scores or makes a diagnosis. Media content is around information filtering, but then also hate speech detection. Cultural heritage is essentially what it says on the tin. So AI systems that might be used in that sector, perhaps to enrich or create metadata description of cultural heritage artifacts, like a cultural heritage collection. And then collaborative content creation is essentially an AI system and Wikipedia editors creating articles together. So this is what we want to do. What we are going to do is we're developing these workbenches and methodologies. So that means that we have some stakeholder research to carry out, and then build and evaluating these tools and processes. We also have a particular remit about training stakeholders in doing an audit and then looking into AI certification. So I wondered, oops, well, that went wrong. Okay. So in the stakeholder research, we're going to touch on various questions. And so what we are going to particularly pay attention to, which I think is really, really important for this community at Viz, is, well, what kind of information do stakeholders need to audit an AI? And really, how do we visualize some of this information that they need so they are able to understand it? So we can't use tools like Fairsight, for example, that are then targeted at these stakeholders. How would that work if we're doing collective auditing? How do we create visualizations that sort of represent individuals within that group, but then are also accessed by everybody? And how do we create visualizations that allow people to feed back about the results of an audit? How can we perhaps integrate a little bit more like interactive machine learning into these tools and these visualizations? And of course, once we build these workbenches and methodologies, we also need to figure out, okay, how do we design and implement them? I mean, for our use cases, there's lots of stuff that we need to know about quality measures, mitigation tools, privacy preserving auditing, and so on. But a major point is also, how do we create these user interfaces and visualizations that might involve some explainable AI, so that people can carry out these audits successfully? So how do we point out problems, but perhaps don't lead them into just focusing on these particular problems that we can specify with the software? So that will be a really interesting problem, I think. So I'm going to wrap up because I think I probably talked long enough. So I think that the key takeaways here is, when you're building visualizations, you need to remember the purpose and the audiences. And until I sort of started looking at fairness and at responsible AI, I felt that I was just creating visualizations. I was creating explanations, but for nothing, for no real purpose, right? They were just sort of like artifacts that were neither here nor there, right? So what I think is that assessment of AI, either predictive or generative, is a really good research area for visualizations that can help people understand what is going on and then assess whether that is good or bad. And then finally, I think one of the major areas that I would think is of importance is the design and evaluation with stakeholders. And I think we need to look outside of the group of people that have perhaps an easier time understanding visualization. So perhaps those without an AI background or without a visualization background. So these naive stakeholders that I have been looking at for quite some time. And I think I'm going to leave it there. I think I'm a little bit over time, but hopefully I have raised some interesting thoughts and I can take questions now.
Thank you, Simone. That was an interesting talk and very insightful for, I really share your sentiment that explanation AI has been going, explainable AI has been going to a different route than we anticipated in the beginning. So yeah. I am going to wait a little bit because we're 30 seconds behind for the stream, but I would like to start by asking what are your thoughts on researchers' role in AI regulations?
Oh God. So I think my particular role is that so my work is bound up with regulation, right? You have to make sure that you know what's coming out, so you can create systems that actually, fit with that regulation. At the same time, more and more, I think that researchers in AI and researchers in responsible AI have a duty to also influence regulation. I think a lot of the regulation is sometimes, a lot of the regulation is currently cooked up by people who don't know very much about AI or how it works, right? So even if we just educate them to better understand what the potential, but then also the problems are with AI, I think that would get us some way there. And then I think that so it's really our responsibility to engage with policymakers as well.
That's a great point. So there is a question with a bunch of thumbs up on the audience Slido. There is a proliferation of many techniques for XAI, creating increasing complexity and difficulty of interpretation. Will the landscape standardize eventually?
So I think if you have complex explanations, then you miss the point of explainable AI. I have to say that I'm getting increasingly uncomfortable with the term explainable AI. I kind of like interpretable AI better, right? Yeah. Because I think, anyone can create an explanation from a system, but it doesn't mean that it's of any use or even understandable. And that's why I'm saying, you have to know the purpose and you have to know the audience, the target group that you want to capture or address with that explanation. So I don't think there is going to be any standardization, right, because I think, different visualizations, different explanations for different contexts for different people.
Right. kind of feel like the field of XAI is kind of dissolving into like mini fields or different directions. It's not a thing. So another question, again with 2 thumbs up, what difference between AI experts and non-technical model stakeholders are most underestimated?
Ooh, that's a really good question. I think a lot in any user interfaces that allow non-technical users to interact with an AI system, if they are developed by AI experts, there is a proliferation of jargon. There is an assumption that people actually know how the system works and what is important in it.
Right.
And so a lot of it is actually down to terminology that is not understandable to non-technical users. I think also there is the capacity for taking in lots of information. I think as computer scientists, maybe there's other user groups, but mainly computer scientists, we are trained to take in a lot of complex information very quickly. Whereas I think you can't rely on that if you're going towards users that don't have a technical background. I think the only exceptions are clinicians and healthcare professionals, because again, they are trained to take in a lot of information very quickly.
That's a good point. Yeah. So going to more towards the theme of this year, in your opinion, what are the special nuances and challenges with evaluating generative AI that makes it more difficult to audit and evaluate?
So I think one of the things is that I think one of the things is that we don't really have good measures of what a good generative AI is, right? So I think we need new measures. We need to get better measures. And some of these will not just be about the model itself, but I sort of hinted at some of them. So questions about the training data, right? There's obviously, well, what training data did you use? Who did it belong to, right? Are there any biases in that training data? And then particularly, I think in terms of assessment, we all know that there are guardrails in place, but we actually don't know what these guardrails are for the most. So we need, again, more explanations about the generative AI system and what its role is and how it's been set up.
Right. I think one of the things that bugs me myself is that there's not really a ground truth per se, as opposed to, a lot of classical AI systems, and that makes it even more difficult because a lot of the classical approaches to measure utility or, those things is completely irrelevant in that context.
Yeah, but also I think, I would argue that even in sort of predictive AI systems, sort of like the traditional AI, the notion of ground truth is really difficult and problematic. So I've dealt a lot with loan applications where ground truth is skewed because you only have ground truth for the loan applications that you actually approved, right?
Right. Yeah.
So
biases in the data. Yeah.
So I think that is problematic, but I agree that some of these terms are so difficult to pin down that we really need to do more research in that direction.
Definitely. I have time for one more question, but there are multiple other questions available too. So what is the advantage of visualization enabled and human in the loop AI assessment compared with computational benchmarking experiments?
I think where stakeholder and human in the loop fairness comes in is that up to now, it was really up to the expert, the AI expert who was developing the system, to choose the fairness metric and the attributes or the features that fairness metric was applied to, right?
Yeah.
And you have over 20 fairness metrics at the moment, outcome fairness metrics, right? So, and they sometimes conflict, right? So the danger there is that it allows the AI expert to optimize against a fairness metric which responds quite favorably, right? So I call this fair washing.
Right.
And you don't actually know whether this is a fairness metric that is appropriate for that context or that many other stakeholders agree with that fairness metric. So that is the benefit of actually involving stakeholders in the assessment, in human in the loop fairness. So you don't have to choose, it's the user that chooses.
That's a good point. Well, thank you so much, Simone. It was a pleasure to have you here and learn from you. Thank you so much for taking the time of your busy schedule. And yeah, if other people have questions in the Discord, feel free to leave them for or comments, leave them for Simone. And with that, I would like to again, pair of applause. I will move on to the next presentation. So, to kick off the paper presentations, we first have Judith Friedl-Knirsch. Sorry if I butchered your name. She is a researcher at the University of Applied Sciences of Upper Austria. And she is here to present her position paper on proposing the use of an Advocatus Diaboli as a pragmatic approach to improve transparency in qualitative data analysis and reporting. Judith, please take it away.
Thank you very much for the introduction. I know my name is not the easiest to pronounce. What I want to talk to you about today is an early concept that for a process for qualitative data analysis. So it's an early concept. It's not a tested or validated framework yet. It's rather in the process of getting there, and this is why I want to discuss it here. So first of all, what is an Advocatus Diaboli, or AD? In English, it would also be translated to devil's advocate. And it's originally an advocate against the canonization of a saint. So it's based on Catholic Church law. And it's a person that argues against another person being canonized or being called a saint. But it has also been explored as a method to avoid group thinking in focus groups. It has been explored to improve managerial decision-making and for finding and defining negative constraints for ontologies to make them even stronger. Furthermore, in qualitative data analysis, which I assume all of you know is analysis of text and video, audio data, or artifact data, we have two epistemologic approaches. They are inherently different based on different philosophical schools, and the positivist epistemology, which is more related to quantitative related science, uses a priori coding, so predefined codes to analyze the text or video data. And the base assumption here is that there is, within the qualitative data, an objective reality that can or needs to be uncovered. This is usually done by more than one person, and then we can create validity through calculating an inter-rater reliability, so how similar the coding was between these two researchers. On the other hand, we have the interpretivist epistemology, where we use emergent coding, which means we base our codes on our data and try to form them as we go. So the base assumption here is that there are multiple ways of how the data can be interpreted, and that the analysis is always dependent on researchers, on their biases, on the framing of the research questions, and what they want to achieve with it. So what are we, or am I trying to do here with this AD process? It's based mainly on the interpretivist version of qualitative data analysis. Because at this point, we often don't have real transparency when reporting qualitative data analysis. There's, in many publications, barely any statement on how the analysis process has been performed. It's also aimed to make this interpretivist research, or this more qualitative, based on constructivism, interpretivism research, more understandable, especially to researchers with a more positivist background. It also aims to provide researchers with an easy to follow process for QDA, which can be on its own quite complex, and to provide a resource efficient QDA process by saving time, by not having to complete the coding process twice by different researchers. So what we suggest is that the first analysis process is performed, I would say, as usual, using, for example, thematic analysis, content analysis, whatever is suitable, and which is led by the main researcher who is also proficient in qualitative data analysis. This is then written up and presented as results to the AD, to the Advocatus Diaboli. And this person then goes back into the data and tries to find statements that refute the results of the primary researcher. This way, they do not have to be as much of an expert in qualitative data analysis. And then the main researcher and the AD discuss the protocol. For example, in the form of a table, we can have a protocol of the findings that refute the or contradict the first round of results. And then we go back into the results after this discussion and decide whether results need to be adapted or whether they will be underpinned by further arguments to make them more understandable, more logically, more easy to follow. The benefits of this process could be that we are saving time resources by avoiding a second complete pass-through, that we only need one expert for a qualitative data analysis, which is, as I experience myself, often hard to have two of these experts in one team, and that the Advocatus Diaboli protocol can be submitted as supplemental material and help with the transparency and with formalizing and writing up a qualitative data analysis process. Another possible future direction could be, and I want to emphasize the could here, to train an AI system to perform the role or to assist the role of the AD, because the primary analysis, the generation of the new knowledge, is still done by a human. The results are also checked by humans, so AI would be in the middle of that process trying to find contradictory statements. So it would never be left alone in a qualitative analysis process. Yeah, and this is already the end of my talk. If you want to see some examples of how I imagine this AD process to be executed or what it could do, please refer to the paper, and I'm happy to discuss this with anyone that's interested. Thank you.
Thank you so much, Judith. Great talk. I am waiting for questions online. Oh, wait, actually we have one. But so to just keep it brief, how do we get reviewers who are often skeptical or untrained on qualitative methods to accept the AD process?
Yeah, for it to be acceptable, it first needs to be tested, reviewed, and checked again and published, of course. So, I mean, this is a first concept. We need to first introduce the proof or publish the proof that this is actually a working process. And that's why I want to discuss it here, because I want to get feedback on that. And then we can talk about how these reviewers will accept that. And I think it's actually a bit easier to accept that if you're more on the positivist side, which I'm aware many of these researchers are, then because there is at least some try to explain it, how we got to the results, which is sometimes difficult with qualitative data analysis.
Awesome. I will ask one more question from Petra Eisenberg. How would you train the AD to give feedback that doesn't feel completely frustrating? What should they not comment on? Where are the limits?
I think the most important part on how we keep this from being completely frustrated is that the AD and the main researcher are in fact discussing this again. So they will talk about it. It's not like an anonymous review where some person can just write everything that's a flaw of your results without ever talking to you in person. But yeah, I mean, there will always be contradictory issues. It will sometimes be frustrating, but it's a social effort, I think, to be as kind to each other as possible while also being critical enough for this process to be useful.
Awesome. Thank you, Judith. This was a great talk and great position paper. You have a ton of questions, so please go to Discord and try to talk to the people who asked them. In the interest of time, I'm moving to the final presentation of the session. Let me share my screen because this will be a recorded talk. So the next presenter is our very own May Elshehaly. She's a researcher at City College of University of London at G Center, and she's here to present Visualizing Lived Experience, Learning from a Master Narrative Framing. Actually, I think I did not share the audio, so let me, oh wait, I did, okay.
Hi, my name is Elshehaly, and I'll start with the first half of the title of this paper, Visualizing Lived Experience. I'll start by giving a rationale for why we started looking in this direction. This was a conversation that started following a series of creative visualization opportunities workshops that we reported on in the last BELIV, where one of the strongest themes, or the strong themes that came out of these workshops with population health experts, highlighted the need to look at public services from the perspective of a person going through the journey rather than an outside perspective. And this kind of sparked months-long conversation with colleagues from healthcare around what they mean by that lived experience element and how they define it. But also we started looking at how colleagues are, we ourselves in the HCI community talk about personal and lived data, And we found some useful definitions of personal data, which is typically captured through sensors. And then the idea of lived data, which adds elements of physicality, emotionality, and social practice to this notion of personal data. One of the very good examples for lived data is Joe's work on visualizing personal experiences with cycling events, where he kind of married data about things like elevation, for example, with the feelings of exhaustion and anticipation of future effort by a cyclist. So the next question for us was, what does this definition of lived data tell us about lived experience? And we found that work by Carpendale and others to be very helpful to our understanding of how people construct meaning of personal and lived experience through introducing subjectivity at different stages of from the data collection to processing to visual mapping and presentation of visualization creation, and sort of how the element of subjectivity gets introduced at each one of these stages. And we identified 4 examples of visualization where this notion of subjectivity, particularly in the context of lived experience, was introduced at each one of these 4 stages. The next step was to explain to ourselves how the authors of these visualizations connected the lived experience of the people behind the data, or the so-called data subjects, with power structures that surround them. And this relationship between the personal and structural is really critical in population health management, particularly in decision-making contexts. So we found a useful theory in diversity science called the master narrative framework, which explains how personal narratives develop within the balance of so-called master narratives. These are typically narratives that are imposed by societal power structures, and then the alternative to that, or alternative narratives, are used by individuals in order to develop their own personal narratives and sort of negotiate with those master narratives. The details of the framework are summarized in the paper, but we were particularly interested in how analyzing elements of content and process from the framework allow people to negotiate as they construct narratives and then manifest those narratives in visualization design. So we asked some questions about how do visualization authors create visual contrast, for example, between a prevailing view on a matter and the missing voices as an example of that reflection. And so we started applying the framework to the 4 examples we identified. And there were some preliminary patterns of the design that emerged as means of catering to specific elements of those sort of content and process in the framework. We offered detailed reflections on these elements of design in the paper, but there's a couple of examples I'm going to mention in this presentation. So this is, for example, from Georgia Lupi's New York Times essay on long COVID. We found elements of conversation with master narratives where she doesn't explicitly, so conversation means that she doesn't explicitly mention or sort of acknowledge the master narrative. The master narrative could be, for example, the one that downplays the symptoms or the impacts of long COVID, but she negotiates with them through conversation, and she uses the politics of at least seemingly hand-written, hand-drawn brushstrokes and marks in order to conduct this conversation with the master narrative. Now, the physicality and the intimacy of hand drawing and the labor that has gone through the process of all the stages from data collection all the way to presentation in her work were used as a tool for that kind of conversation in her essay. Another example, probably on the opposite side of the spectrum, is Mona Shalaby's Gaza collection, which presents an example where that labor of data collection and processing wasn't there. But even then, the lived experience of those behind the data was visualized in a way that presents a deviation from the master narrative that reduces, for example, human life to numbers. So she acknowledges the existence of this master narrative, and this is where deviation kind of changes or varies from conversation. And through acknowledging this master narrative, she presents data as an antagonist. So she kind of takes that character-oriented design of visualization where signs of data life or how life should look like explicitly define those data squares and do not really fit within them. So we kind of thought this was an element of deviation from a master narrative according to the master narrative framework. We also found the work on idiosyncratic timelines useful to reflect on how shape and position, for example, were used as tools of alignment and negotiation between individual stories and global circumstances. And finally, this example from BizApp on sexual harassment in academia was also very useful in revealing how things like color, for example, can be used to encourage the process of evaluation where individuals can identify with a specific view or position and evaluate their own internalization of the master narrative through that. There's more reflection in the paper, but one can conclude that the master narrative framework offers an opportunity to connect the personal to the structure. And then the next question for us is, well, how can we design visualization for specific elements of conversation, deviation, and other components in the framework? Obviously, we've touched upon this in a very preliminary sort of reflection in the paper, but there's a lot more to that work that we would like to do in this space. Visualization can also contextualize data with lived experience, which is good news for us. We've seen those examples mainly for advocating for an idea, but then the next question for us is going to be, well, can it shape person-centered policy? Can we actually use this to inform policy makers? And with that, I will end my talk, and I will be very happy to answer any questions, but also hopefully discuss with you during the breakout sessions. Thank you very much for listening.
Okay, so for some reason I can't start my video, but great talk, May. Oh yeah, there, I can do it. Great talk, May. I'm waiting for a second to see if there are any questions that we can ask, but we're also short on time. Let me see. So I guess like more of a general follow-up question for the future. How do you see this applied in the wild? Like, is this something that, I mean, some of your examples look like things have been already happening, and you have great examples in, you know, from real world, but do you see that, you know, this kind of framework being used in the wild, and especially for like journalistic perspectives or versus the political perspectives?
Well, that's a great question. The answer is I don't know yet. We're still sort of scratching the surface in terms of what this kind of framework can help us understand, first of all, about existing visualizations that are in the wild. So some of the examples are, you know, just kind of from journalism. Some of them are from papers. The thing that we're really keen on is to try and work out actually how does this also help us co-construct those narratives with the people in the data. So one of the things I'm really interested in, particularly from that population health perspective, a lot of the decision makers and the sort of stakeholders that we work with are always keen on getting those voices into the data visualizations. They simply hate dashboards. Every time we give them a dashboard, they're like, yeah, but there is, you know, people behind this who will tell you otherwise. One of the very famous examples we always use is about autism, you know, people underrepresented in the data and a lot of sort of implicit error. So yeah, we're hoping we can sort of use this to bring those voices in and really start co-constructing those narratives with people through visualization.
Yeah, this I really enjoy your paper, and I also think it's a very timely and important paper and topic. Thank you so much for taking the time. I don't see any questions in the poll yet, and we're also 2 minutes over time. So please, if you have any questions for Mai and don't have time yet, we will have more discussions towards the end of first session in the breakout rooms. Yeah, thank you so much, Mai, and thank you to everybody who presented in the session. I'm gonna wrap up the session. We'll be back after the break.
Seems like it's time to get going. I see a lot of nodding, so this looks like a positive signal. Welcome everyone to the second session of today's BELIV workshop at IEEE. The break is now over. let me very quickly introduce myself. My name is Jürgen Bernhard. I'm assistant professor at UZH in Zurich. I have had a very long tradition in visual analytics. First about time series when I was still at Fraunhofer in Darmstadt, then in interactive machine learning. This is when I sort of got in touch with data labeling quite much. I came back to visual analytics, quite intense, together with Tamara at the UBC. And then finally, yeah, once again, made it to the Alps in Switzerland. This session is about experiments and evaluations. And afterwards, we will have a breakout session, so don't run away. A little bit of a teaser regarding what will happen. First of all, we will see a very interesting approach where actually a contextual inquiry study was conducted. And we see how the substitution of words can lead to quite some different results in a proxy on sentiment analysis. We will make a deep dive into signal detection theory and see how that can actually connect to lineup tasks for assessing visualizations. We will see and learn about the role of visualization literacy in empirical studies in visualization. And finally, we will learn a lot about stress or normalized stress, and a new version of measuring normalized stress in a scale invariant way. This is the 4 papers that will be presented in the next 40 minutes. Afterwards, once again, the breakout session. And this brings me directly to the first speaker, which is Anna Crisan. She will this is the breakout session. I will now stop my screen share such that Anna can actually do the screen share on her end. And while she is setting up, I can tell you that she is actually interested in contextual counterfactual explanations, and the title of her talk is Exploring Subjective Notions of Explainability Through Counterfactual Visualization of Sentiment Analysis. Looking forward. Floor is yours, Anna.
Okay, great. Thank you very much, everybody. So I am presenting this work on behalf of also my 2 other colleagues. We did this work while I was still at Tableau and now at the University of Waterloo. So this motivation for the work that I'm presenting here today came from an earlier study. So also with my colleagues at Tableau and Salesforce, we did some research on something that we called interactive model cards that we published at FACT in 2022. And there was a lot that was going on here, but one particular component of this interface was to allow people to essentially add their own new data as a way of testing how the model would perform on something that was potentially outside of its training data, potentially outside of its testing data. And this little part of it presented some really interesting problems. So here is one challenge that we actually discovered when we made this available and that we found ourselves. So here we have a very basic sentence that we have typed, which is the main character is a trans woman. And this particular model that we were assessing was a sentiment analysis model, and it returned that it had a negative sentiment and that the model was quite confident with this. And then we allowed people to provide some feedback on whether they agreed or disagreed. So then all that we did was change the word trans woman to woman, and the sentiment flipped. It was a positive sentiment with much higher probability. And then we, in fact, changed woman to man. And it still remained a positive sentiment, but with an even higher probability. So this was a very interesting experiment. And we actually went ahead to try to figure out why it was doing this. And it turned out that the model has a problem with hyphens. It interpreted hyphens as negative. And so if you had the word transatlantic or any hyphenated word, it automatically produced a negative sentiment. But of course, for many folks in the LGBTQ community, they would somehow be impacted by this behavior. So this research was really, that I'm talking about here, was a way of actually going further, of looking at explanations and looking at particularly people that might be impacted by these AI/ML models, and taking a look at the efficacy of explanations that are produced so people can perform the same experiment that we did as researchers. So we wanted to ask whether some of these visualizations actually worked for people that were not data scientists or machine learning researchers. And one particular reason that was really important to do this came from a quote from one of our participants, where she talked a lot about how explainable AI, or the notion of explainable AI, is defined by computer scientists, which is really looking at it as an object to be understood. And she wanted a sort of a more humanistic way of thinking about XAI, which was not thinking about it as an object, but as a mode of communication. And this came to be a really prescient observation. As you'll see with our study participants and some of the quotes that I share, this communication aspect was critical in actually understanding how the model was working. So in this very narrow context of sentiment analysis, we actually developed a technique that would automatically generate counterfactuals based upon just single word permutations. It was a very simple idea, and we weren't relying on the user to provide, different examples. We would take a look at a word you wanted to replace, the context of the word, and try automatically do that for you. And we paired that with an interface. And we use this as essentially an instrument. So we're not contributing a system. We used it as a probe to help us through our contextual querying studies, which was, in this BELIV paper, very formative. So we conducted expert interviews. First, I'll show you the interface. So the very base case that we started with most people was what you saw in our interactive model cards, which was somebody could type in a sentence. In this case, the film was filmed in France, and it just provided the model's output that it was positive. It provided a number like 96.52% positive sentiment. And then we translated this into a word score to words that said that the model was almost certain that this was a positive sentiment. So we augmented this then with an XAI technique. In this case, we used Lime. If you want to know why we use Lime, take a look at the paper, because there are obviously others. And basically what the Lime is doing is it's adding a visualization that would then take a look at the relative contribution of each of the words in the sentence and how much it contributed to sort of the positive sentiment versus the negative sentiment. So this was the base case, no counterfactuals involved. We then explored the counterfactual case. So we had different methods of actually sampling across the counterfactuals produced. So in this particular example, we chose, the original sentence and we contrasted it with the most extreme positive result and the most extreme negative result. In this case, also using the text case, right? So we actually, because it was a country, we substituted every single country in the world for one of those words and just, got the actual distributions. And then, of course, we also included the Lime explanations as well in the counterfactual case. These were 4 cases that we tested. In this case, the counterfactuals were just sampling the extrema. And then we had a 5th case that we showed people, which was a scatter chart that was showing the distribution of sort of sentiment and model probability across every single possibly counterfactual that we could generate for that particular statement. So this would show every single country and where France stood relative to others. Okay, so this was the instrument that we used, and we tested it with 10 participants that all were using like AI in some capacity in their job, right? And they were interested in explainable AI, but they were not necessarily computer scientists. There were some in the mix. And they were not necessarily people, even the computer scientists that were using explainability tools like Lime or SHAP regularly. Some were, some were not. They were also distributed across industry and across academia. So there were 4 key themes that emerged from our studies that I wanted to talk to you about today that was really important in helping us understand the subjectivity that comes in understanding explainability and its role. So one was just the attributes of an explanation that would influence people's perceptions on accuracy, trust, and fairness. The other one was their understanding of when they would actually apply it, which was actually very important. So if they couldn't understand how they would use it, they didn't necessarily care that they had an explanation. There were also contextual factors, and this was where the most subjective notions of explainability came in and influenced the title of this particular paper. And then finally, there was their existing processes and how they would actually integrate counterfactual examples. This was different than applications because it wasn't just here's how I'm going to use it, it's more here's where I'm going to use it. So let me tell you what our participants told us. These are quotes from different participants in the study. And so when they talked about the explainability attributes, a big part, especially if they were a computer scientist or data scientist, was needing to take this explanation to somebody else. So somebody talked about how hard it was, looking at these examples to sort of sand down the noise. As we would see later, counterfactuals were actually useful and important in doing something like that. From the examples, a lot of people suddenly figured out, hey, this model might have a bit of a Western bias because all the European nations have a positive sentiment. folks also saw the counterfactuals as a really useful and intuitive way of helping them to contextualize the results based on their background. They were also, when they saw the range of the model's responses, shocked by some of the model's certainty. We did do some follow-up kind of crowd work studies, and what I found interesting is when people saw how biased and bad the model was, they thought that we were tricking them into giving them a bad model. And I tried to explain to them that this is a widely used model downloaded often 1 million+ times a month from Hugging Face. When people were looking at their attribute at the application, they were again thinking of who they work with. So we had a marketing manager that had to work use AI, but needed to explain it to other people in her organizations. And so education was a really big application area that emerged from being able to use counterfactuals because people could see the responses and play with them and get a sense for what was going on. For data scientists, it was actually also valuable to see the counterfactuals and doing this at scale because having to manually think of them was very hard for them. But the whole part of the application that was generally powerful to people was being able to see a variety of these different responses and sort of situate the one particular answer for their query with possible related answers for other queries. The contextual factors are really important because we actually tried hard to recruit people that were non-native English speakers. And so it was really important for people to kind of, when English was not their first language, comparison was a useful mechanism for them to say, hey, why? Like, what's going on here? It gave them different avenues to engage that they might otherwise not think of or have the ability to express. So saying, why is this different is simple and is a starting point. And many participants point out that this is really useful for helping understand like why the model is weird and why it's doing something weird, and also allow for different cultures to try to interpret it themselves. And this idea of seeing many, many examples was particularly salient in being able to drive skepticism towards the models and increase these notions of like, is this even fair? The last theme that sort of centered around process was really was much more a little bit like mechanical, thinking about the visualizations, thinking about their workflows and the way that they could actually integrate it. And this is where combining automation, perhaps ironically, for explainable AI, with visualization on top was really powerful. So this automated ability to see everything was very helpful in promoting, transparency in what the model was doing. Participants saw different values and different ways of communicating information, some that were better at communicating accuracy and others that were better for transparency and trust. But all felt that the more that you exposed them to visually, the better that it was. So this is a whirlwind tour and a very high-level view of all these different themes that emerged, and I encourage you to look at the paper for final results. I'll just wrap up to explain some design themes that came, or some design guidelines that we sort of extracted from these different findings, which was that it's actually kind of important to take these cultural factors into consideration and design personal explanations with guardrails. That it still was important to balance information density and reduce cognitive load. The scatter plot was overwhelming for people. That multimodal explanations, or basically saying things in different ways, can be powerful. And that incorporating contrastive examples is actually really useful during the design process to surface these issues. So briefly to conclude, explainable AI is not well tailored for folks that don't have a data science or machine learning background. We did find counterfactuals were a powerful way to augment XAI techniques, and they are an XAI technique within themselves. Comparison was a powerful mechanism to reach across cultures and backgrounds. Visualization was useful. And the last one is it still is really helpful to use proxy tasks like sentiment analysis to study more complex scenarios, but further research is required. Thanks very much. And if we have time for questions, we might not. I look forward to answering them.
Thank you so much, Anna. That was great. Thanks for all these takeaway messages and observations that you made. By the way, also thank you for sharing your study materials in OSF. I had the chance to go through the video this morning. It was great, a great experience. And also your scatterplot idea about the comparison of results is just fantastic. It's fun. It's really fun. Thanks for that. Short question from my end. You said that your machine learning model was just a proxy for an overarching idea that you're studying. What other types of proxy usages, maybe regarding code generation, but also others, could you imagine?
Oh gosh, it's a complex one. So sentiment analysis is a useful task because it's something that people can easily understand without a ton of explanation. It's a classification task, sort of yes or no. And so it's sort of useful to get a base sense of at least other clustering or classification tasks that people might perform, even more complex tasks in that area. And that actually covers, as you know, with labeling, a wide variety of common machine learning tasks. Once we start to kind of go outside of that and talk about, you have to actually predict a number, or you're trying to do something more generative, it can start to get a little bit more complex. But some of the ideas like cultural backgrounds or things like that are using simpler tasks can help these sorts of ideas emerge earlier on and allow you to start to consider them when you are looking at these more complex tasks. So I don't know, for code generation, maybe people have a certain style and you can pick something like that up earlier, rather than as a summative study when you actually assess your tool.
Got that. I guess we'll come back to you given the great opportunities. I will read a question that comes through Slido, and I like this one because it also aligns with the overall theme of our this year's BELIV. When they saw the biases, they thought they were being tricked. That's, of course, a nice one. Does that mean that people largely overestimate model fairness in the wild?
I think Mashan has done actually very interesting research on this as well. So everybody comes with sort of, I think, a certain base alignment of how much they might want to trust a model or not. And I've seen this in the wild in many places. Some people are overly trusting of a model, and some people are skeptical no matter what. It's actually more challenging to find people in the middle that are quite nuanced. It might mean that for a lot of people, they are overestimating how good a model is. And it was such a surprising thing to me when people were like, why did you give me a bad model? It was a shocking result in finding. It came out in the crowdsourced stuff. And it actually, at least to me, whether you're overly trusting of a model or you don't trust it enough, it actually went to go and say like how valuable it is to sometimes show the variance in the model results in a human comprehensible way, in order to elicit some of what I think is a healthy skepticism. So I think in the interactive model cards paper, we talked about productive skepticism. And I think that's generally what I'd like to promote. I don't think we should throw the baby out with the bathwater and say all ML is bad, but I also don't think that we should just accept it at face value either.
I like your response also that it sort of connects to the keynote that we heard a couple of minutes ago.
Yeah.
Very nicely taken. Thanks for that. Anna, thank you again. And we proceed to the next speaker. It is Shen Long. Maybe you can already start sharing your screen. In this case, it will be a played video. Mashan will take the action for this. I can announce the talk in the meantime. It is now from Counterfactuals coming to wine, old wine in new bottle or not. This is the question. Analysis of visual lineups with signal detection theory applied in this case for color maps. That's something I can already spoil.
The title is Old. Hello everyone, my name is Sheng Long. I'm a PhD candidate at Northwestern University, and this is a joint work with my advisor Matt Kay. The title is Old Wine in a New Bottle, Analysis of Visual Lineups with Signal Detection Theory. Let us start with a question. How should we design experiments to test for the correct detection of visual signals? Prior work has proposed a lineup task, which has its name inspired by the criminal lineup. In this task, one plot is drawn from a dataset, while the remaining plots are drawn from another dataset. And the task is to figure out which image is the odd one. And if you ask me, I have no idea which one is odd, even after spending some effort. Similarly, this is also a lineup task, where participants are asked which image does not belong, or are the images indistinguishable from each other. Here I can say with confidence that the plot on the bottom left appears different compared to the other ones. Both of these tasks are lineup tasks, yet there are differences between them. The first difference is that in the first task, we don't have the option to select no difference detected, while the second task gives us this option. The second difference is that data is always drawn from two different datasets for the first task, but for the second task, data can be drawn from the same dataset. A third difference is that the second task does not collect confidence ratings from participants, while the first task does. We started with the question of how should we design experiments to test for the correct detection of signals. I showed that even for relatively simple tasks, there are differences in how one can administer these tasks. These experiment design choices have downstream influences on how we can analyze data collected from these experiments. Further, from the first task, it is unclear whether a participant selected the wrong answer because they decided to randomly select or because they genuinely perceive something to be different. So more generally, how can we separate perception from decision when designing and analyzing experiments? Now, prior research in psychophysics have proposed a method known as signal detection theory to study these questions, and our position is that we should analyze lineup data using signal detection theory. We demonstrate the utility of signal detection theory by applying it to prior lineup data collected by Reda and Zafir. Our analyses provides additional insights for why rainbow color ramps do not increase false discoveries despite their undesirable perceptual properties. But first, what is signal detection theory? Well, it is a general psychophysical approach to model performance as a function of sensitivity and bias. The key assumption of signal detection theory is that the strength of sensory and cognitive events is continuously variable. In its most basic form, each observation is a random variable drawn from one of two sensory distributions, signal absent or signal present. Because these sensory distributions overlap, error can arise. And the solution is to divide the sensation axes into two regions with a criterion such that high values lead to, yes, I perceive a signal responses, and low values correspond to, no, I do not perceive a signal responses. Fixing the distances between the two sensory distributions, our participant can have a high criterion, which translates to a conservative bias, meaning that they are more likely to respond no difference detected when answering a lineup task. Likewise, a participant can set a low criterion, which translates to liberal biases, which means that participants are more likely to respond yes by selecting one of the 4 plot options in a lineup task. Fixing the two sensory distributions and the location of the criterion, the shaded area under the signal absent distribution is the false alarm rate, which is the probability of selecting one of the 4 picture options despite them being drawn from the same dataset. In other words, it is the probability of claiming to sense a signal despite it being absent. The shaded area under the signal present distribution is the hit rate, which is the probability of selecting one of the 4 picture options when they are drawn from 2 different datasets. In other words, it is the probability of correctly detecting the signal when it is indeed present. We can transform the hit rate and false alarm rate using the probit function, which is the quantile function of the standard normal distribution. This allows us to define sensitivity as the difference between probit transformed hit rate and false alarm rate, as well as criterion, which is the sum between probit transformed hit rate and false alarm rate divided by -2. Using signal detection theory, we found that while an average participant is most sensitive to the rainbow color ramp, they are nevertheless more likely to respond no difference detected for the rainbow color ramp. Our findings suggest a potential explanation to reconcile the conflict between the undesirable perceptual properties of rainbow color ramps and Reda and Zafir's finding that they do not increase false discovery. When running experiments, we have direct response variables as well as model-dependent response variables. Examples of direct response variables include accuracy, response time, and precision. Examples of model-dependent response variables include sensitivity, bias, and psychometric functions. While model-dependent response variables enable us to make more precise claims, they come at a catch, and the catch is that they typically require more data and more complex experimental designs. We also think it is important to consider the role of model building in visualization research. As a discipline, Viz has received influences from multiple other disciplines. One thing to consider is whether we should model things more like economists, who tend to take a more top-down approach, or more like psychologists, who tend to take a more bottom-up approach, or perhaps a mixture of both. To conclude, we can use signal detection theory to better analyze data collected via the lineup task. Signal detection theory allows us to separate perception from decision. And as Viz researchers, I think it is important to consider how we should approach model building going onwards. Thank you for listening. Please check out our paper for more details.
Thank you so much, Sheng. I would very much like to point towards this particular type of flavor that you introduced with the signal detection theory, because this is somehow what makes your approach so special, if not even unique, at least in the visualization research community. I also would like to tailor my questions more or less around this. Before I start, thanks for also making your research available at OSF. That is very much desired. I also took from there your image that I also showed in Discord. Question is about generalizability. So there is someone who is not that much of an interest or not that much of knowledge in that particular type of things, which are domain foreign, and would like to sort of do the same thing as you did. So do you have any guidelines for normal visualization researchers to apply your method? Which obstacles do we have to take?
I think it really depends on, and I just want to make sure that you can hear me all right. Yes, cool.
Good.
Yeah, I think it really depends on the kind of data you collect. As I said, it really depends. You have to set up your experiment a particular way so that you can then perform a signal detection analysis on top of it. So I think in terms of how generalizable this approach is, as long as you set up your experiments in the right way, it should be very generalizable to the right kind of data. But if it's not set up the right way, then there are certain assumptions that this model relies on that you cannot apply to.
Got that. There is at the moment still no question coming from the audience. Let me quickly ask you if you are already elaborating on alternatives to color maps.
Yeah, so this project really started as us trying to, look at the polar versus Cartesian coordinates. And I have to say, I'm very, very grateful for the Rainbow Revisited paper by Rita and Zafir, because without that paper, we would not be able to even perform this analysis. So big shout out to them for putting their data and their, experiment protocol out there. Yeah, I generally think that the lineup task is very interesting because it somehow combines, elements of statistical decision theory and really lets you think about how exactly do we extract signal from noise. So yeah, it would be interesting to see what kind of further extensions we can then apply.
Like that summarizing statement, separating signal from noise. Isn't that what we all are doing in the visualization community? Fantastic. Thanks, Sheng, once again, which brings us then to the next talk, the third one, which is from Abhraneel. And we are dividing from wine towards something very different. It's now about telephones. And the talk is screen shared in just a second, and its title is Task a Telephone, Understanding Barriers to Inference Due to Issues in Experiment Design. Let's see what the telephone framework is like. Floor is yours.
Right. Can you hear me?
Yep.
Okay, awesome. Thank you for the introduction. So I'm Abhraneel.
Abhraneel, I think you're sharing the wrong screen.
Oh, am I? Shit. There should be, oh.
Thanks, Sheng. Yep. Perfect now.
Awesome. Cool. I'll start from the top. So I'm Abhraneel, and I'm going to be talking about this paper, which is a position paper. And as you can tell from the title, this is about some of the assumptions that we often make in experimental design, which may or may not be valid. And this is work done with co-author Sheng, Michael, and Matt. my advisor. Okay, so before we begin, let's I'll start with an example. So this is an experiment which is adapted from an actual experiment that was done by Les Padilla and co-authors, which is where they ask participants to imagine that they work at the Red Cross, and their job is to issue blankets to alpaca farms in Peru when the temperature is below freezing. And to help them make the decision, they're given a nighttime temperature forecast, and they have to decide whether or not to issue the blankets to the alpacas. And the nighttime forecast looks something like this. It could look something like this, or it could be some other distribution, but this one is a cumulative density function of a temperature distribution. And based on this forecast, they have to decide whether or not to send blankets. So let's say that the task that the experimenters want the participants to perform is that they should send blankets to the farm if the probability of freezing is at least 20%. However, participants might be actually performing a different task, which is which we denote as T prime, which is that they send blankets to the farms if they think it'll be cold in the farms in Peru. And this is because, as you may have realized, that the number 20% was not actually communicated in the instructions to the participant. Now, obviously, this is a very strawman example, and I would like to mention that this is not this is not what Les actually did in her study, but it highlights how there might be a discrepancy between the tasks that experimenters want the participants to perform and the tasks that participants are actually performing. In our paper, we actually provide examples of actual studies where we think such discrepancies exist. And so we use such discrepancies to come up with a framework, which we call the telephones framework, and I will describe why so in a bit. Anyway, so in visualization experiments, we give people a task and we give them a visualization to perform the task, and we expect that they will use this, they will be performing the task that we want them to perform. But what might happen is that there's a discrepancy and they actually perform what they think the task is. An explanation for why this might be happening comes from recent work by Carolina Nobre et al., which is related to visualization literacy. And they find that people often misread a visualization, or like they fail a visualization literacy question because they often fail to translate what the task is. And they term these as translation barriers, and they identify two types of these barriers. Anyway, so let's move on back to our example, and let's assume that we, as the experimenters, did not provide the participants with any explanation or any guidance on how to interpret this visualization. The CDF, we as visualization experts know we can start with the x-axis where we want to read the graph from, and then we can project that on the y-axis and get a probability value. So this is the strategy for reading the graph, but the strategy that participants might actually be using is something completely different. It could be that they're using probability of freezing by comparing the area under the curve to the left of the 32-degree marker from the overall area. So this highlights the second issue that we identified in this framework, which is that experiments often assume that participants are always performing the task using the optimal strategy for performing the task with the visualization. But what might actually be happening is they might be using a strategy which they think best supports the task T prime, which may or may not be the actual task. Again, the work by Nobre et al. Identifies a few barriers which might explain why people are using a different strategy. And some of these include like misunderstanding the visual encoding, misinterpreting the axis, etc. And then finally, just to round off, they also identify a set of decoding barriers, which often which would in our framework translate to the ability to execute the strategy that they have identified properly. So what does this mean? So when we think, what we think we're measuring when we're conducting an experiment is that we give people a task and a visualization. They would perform the task using the optimal strategy for performing T, and we get a measure of effectiveness, which is how well does the visualization V support the user in performing the task T using the strategy, which the experimenters think is optimal, which is S. But what might actually be happening is that we're measuring some other construct, which we don't really care about, but is how well does the visualization V support a user who thinks they're performing T prime in performing the task T using the strategy S prime. And very quickly, this resembles a game of the children's game of telephones, which is why we titled the paper as such. Okay, so the primary takeaway of our paper is a set of guidelines for experiment design. Obviously, this depends on what the objectives of the experiment are and what claims the authors want to make. So for instance, if the objective of the study is that the visualization V is more suited for any task T than another visualization V prime, then we want to make sure that participants are performing the task that we want them to perform and not some other task. And one way of doing this would be to conduct pilot studies to ensure that minimal task under misunderstanding is occurring, and also demonstrate that participants understand and are performing the tasks we want them to perform. So when we're doing these pilot studies, we should conduct them with the actual population and not a convenience sample. Another way could be to use collect qualitative responses on how participants are performing the task. And then another claim could be that the author wants to make is that a user is able to identify the optimal strategy S for performing a task with a visualization V. In this case, the experimenter needs to ensure that all participants have comparable understanding of the visualization and what it is encoding, in addition to steps taken to ensure that they're performing the correct task. We argue that good instruction writing and introductions and tutorials can help with this. And finally, one possible claim is that how well a user is able to execute the optimal strategy for performing a task with a visualization. In this case, the experimenter needs to ensure that almost all participants are actually adopting the optimal strategy. Two ways to verify this could be to ensure to provide training and feedback so that participants can make sure that they're identifying the optimal strategy, and verifying by eliciting and analyzing qualitative responses of what strategies they're actually adopting in performing the task. Again, this is not an exhaustive list of how to address these discrepancies or potential discrepancies, but these are some of the ideas that we could think of. And anyway, with that, I'd like to thank you for your attention.
Thank you, Abhraneel. That was super exciting. And the question that I prepared got partially addressed. So I want to ask this one a little bit more in depth and to get it clarified. I wanted to ask you how visualization literacy can be characterized. Are there dimensions by which we can sort of characterize types of literacy or degrees of literacy, visualization literacy? And I find that your framework gives already quite a good answer. Especially with the encoding and the decoding component, which I particularly like, given all these entropy things that can happen along these lines. Can you unpack that a little bit more, if that can be used for a characterization?
Yeah, I think so. There's a lot of work being done on literacy, and I think one of the things that actually some of my lab mates are probably better, they're more informed about literacy, and they would probably be better at answering this question. But often it seems like literacy is viewed as a singular construct, which may or may not be the case, right? Like literacy, there might be, just like we have, numerical literacy and like some like English literacy or whatever. I think in terms of visualization, you might find that literacy is more multifaceted, and I think which is why I think we had a graph in the paper which shows that, like, the relationship between literacy and like how people perform on a task may not be linear, or it might just be very chaotic. So I think it's hard to answer that question directly, but like I think we need more understanding of literacy in the context of visualizations. I think that would help us answer that question.
Yeah, I can clearly see your point. Thanks for making that more clear. There is 2 more questions, and I'm asking you to be part of the Discord such that we can proceed. Try to stay in time, and I'm thanking you once again, Abhraneel.
Okay, thank you.
This brings us to the 4th and last speaker. It is by Jacob Miller, and we are now diving deep into normalized stress. And you may or may not have known that normalized stress measures for dimensionality reduction are typically invariant, problematic for scaling issues. And this is going to be solved in the next 10 minutes. Floor is yours, Jacob.
Great. Yes, thank you for the introduction. So I'm Jacob. And I'll be presenting a paper we worked on. Normalized stress is not normalized, and we'll try to teach you how to interpret stress correctly. A quick note, presenting on behalf of my co-authors, Kiran and Stefan. When we started this work, we were all at the University of Arizona, but since 2 of us have in whole or in part moved to Munich. So I wanted to give a quick overview of the points I'll be trying to make today. So on the bottom row here, I have 3 projections of some high-dimensional data set. They're shown as scatter plots. And I've taken some measure, stress, of their quality. And in the top plot, I'm showing, so each of these projections is a curve in this plot. And just by changing the size of the drawing, I'm getting wildly different values for this quality metric. So let's first try to define what we're working with: high-dimensional data, which I'm calling a collection of features that describe some objects, for instance, penguins. Typically, there's more than 3 features, which makes it difficult to conceptualize. But for instance, if we have some physical objects, we can break it down into maybe component parts, for instance, flipper length, bill depth, or body mass of a penguin. And once we have these, we can table them or put them in a matrix, so that each row in this table corresponds to some physical penguin and its attributes on the columns. But this is difficult to understand with just looking at all these numbers. So what we often like to do to get an overview is to perform dimension reduction into 2 dimensions, for instance. Here, we can kind of get a sense of the structure of the data. We would like this projection to maintain some data properties, but different algorithms do different things. So if I show you 2 different projections of the same data set, like here, you might ask which one is better. The one on the left is kind of elongated and not very distinct between the blue and the green. And the one on the right has nice round clusters, but I might have lied and just colored them to make it pretty great. So what we do is we compute quality metrics that kind of tell us that this drawing preserves this quality more than another projection. And today we'll be talking about stress. So it's defined by this scary looking equation here, but I'll try to define it more in words. It's a measure of difference between ideal, or in this case, high-dimensional distances that we've taken from the input data, and we're contrasting it with the realized distances in our projection. So we take pairs of data points, we measure how distant they were in high-dimensional space. We look at our projection of the same pair of data points. We look at how different they are in low-dimensional space, and we compute this red bar distance shown here. And we sum this over all theirs in the data set, and this gives us a number. Right, but when we're given a projection, the computer representation of the scatter plot is in some arbitrary units that we've used to encode the relationship. And we know as visualization designers that there's kind of an implicit transformation we have to use when we're plotting this. If my units are given in a range of a 0 to 1 box, for instance, I have to convert these to pixel units on the screen somehow, right? And I'm illustrating this by showing that I haven't given you the range of this axis. And so the representation units may be very different than the high-dimensional units that are encoded. And I claim that when I'm computing a quality metric, these units shouldn't matter, whether I choose to draw the projection very small, like this, or some medium size, or 100 times as big. My metric that tells me what the quality I'm preserving shouldn't change. But in fact, stress does. I've shown here some example numbers about how bad can it be. Well, we can take these three projections of the same data set again. You saw two of them earlier. The one on the left is an MDS projection, which is explicitly optimizing the stress function. The middle is a t-SNE projection, which is doing something completely different, but it's still doing something intelligent with the data. And the one on the right is a uniform random distribution of the points, so there should be no correlation between the projection and the data set. But again, when I measure normalized stress and I vary the scale, or vary the size of the drawing, or the projection, the number that normalized stress gives me is quite different, and in fact, vary along these curves. And if you notice, for instance, that if I wanted to pick my favorite projection algorithm, and normalized stress is the lower the better, I can find on any point in this graph a scale value where my favorite algorithm is 1. So we don't like this property. We did a partial survey of some of the dimension reduction visualization literature and categorized some variants of stress that are used. Many more exist. We didn't talk about raw stress today, but the behavior is not that different. And we showed normalized stress exhibits some poor qualities. 3 alternatives that we also identified from various the parts of the literature that are scale invariant, but I'm not going to talk about scale normalized stress today because it's very simple. And if you want to hear about the other ones, please read the paper or add me on Discord. I'm happy to talk about it. But what we're calling scale normalized stress is this quick fix for normalized stress. I have several projections I want to compare. And each of these projections defines a scale curve as shown here. I ask, well, which scale value should I compare with? Well, I should pick the minimum. And these are quadratic curves, so this is straightforward to derive and compute. So in this case, each projection might have a different scale value that we're comparing against, but it's always the one that gives the minimum normalized stress value. This originates from sort of the network visualization literature, where it's kind of known through private communication. It is also not extremely well documented there either. So a good question now is this an abstract problem, or is this effective in previous evaluations? We took a look at a dimension reduction survey for visualization. It's quite recent, it appeared in TVCG. And this is a very nice survey. And one of the things they did is that they took lots of different data sets and lots of different algorithms and computed projections for each of these dataset algorithm pairs. And then for each of these projections, they computed lots of quality metrics and analyzed the results. And one of these quality metrics was normalized stress. So our basic goal is to see if results change when we employ scale normalized stress instead of normalized stress. So we took a subset of these algorithms. On the columns of this table are algorithms, and on the rows are data sets. And we've shown the ranking here. So from 1 to 5, worst to best, using normalized stress. We see the trend is from MDS over to t-SNE. It sort of gets generally better to worse. But we instead use scale normalized stress. The story is quite different. In particular, t-SNE seems to have gotten not quite a fair shake, in that while it was almost consistently ranked the worst using normalized stress, it's in fact achieving second or third in scale normalized stress. So in conclusion, you shouldn't use normalized stress to compare 2 or more algorithms. There are 3 acceptable alternatives that we identified: Shepherd goodness score, non-metric stress, and scale normalized stress. Again, we talked about one of them, but the other 2 appear in our paper. And what I didn't mention is that this Espadado survey provided open access to all of the embeddings and code that they used to produce these. So it was critical to our evaluation to be able to verify this evaluation. So a big shout out to these authors. Our code is available through a quality metric library called Zadu. So also thank you to the Zadu authors for cooperating with us in implementing these in line. For future work, there are other quality metrics that are sensitive to scale, for instance, scale divergence, and perhaps others. We also might want to validate past results that rely on this normalized stress computation. And as a kind of a broad open question to the workshop is how can we reliably evaluate quality metrics for visualization? But that brings me to the end of my talk, so I'm happy to take questions now.
Thank you very much, Jacob, for this excursion into dimensionality reduction land and its associated metrics. We are a bit over time, so I will only ask a very short question, and then we can talk afterwards. My question would be the following. Stress measures are used for two things. First of all, to assess the quality afterwards, but also as an optimization criterion while training an iterative process.
Yes.
Regarding the latter, do you think that this kind of improvement can also be used for interactive machine learning-ish iterative model training of DIMRED?
So, if I understand the question, I think you're asking is normalizing by the scale potentially affect optimization? Yes, so my intuition is no, but I know there are some like deep learning. So in the graph drawing world, there's some deep learning papers that for some reason needed this sort of what they call canonicalized version of stress to accurately reproduce nice drawings. So potentially, yes.
I will leave that open as a frame of thought, possibly interesting to study further. I will close the session with that. Thank you, Jakob, as well as all the other speakers as well. I thank the audience, and I'm now sharing my screen to make clear that we are now moving to the breakout activities. And this time my screen share works. In the intro, it did not. Bad luck, but never mind. You are all invited to join the breakout activities. It's 3 different sessions: AI modeling and explainability, evaluation and methodology, as well as user interaction and perception. See you there and have a great time. Thank you.